W, S, E, and A. So as in all monads, the last one is always the result type. So the A is the overall result of the computation. I will get to all three of the others in due time, but I briefly want to go through them now, just to give you an idea what they're for. So the W is like in the writer example I gave you. So it allows a contract to write log messages of type W. So in our example of the writer, it was just list of strings, but here you can specify some W. And I did say log messages, but the purpose is not really logging. The purpose is to communicate between different contracts. So the written W is visible from the outside. So this is a way for a contract to pass information to other contracts or to the outside world. The S specifies the endpoints. So what endpoints are available in this contract. And the E is the type of error messages. So similar to our examples of maybe and either, in particular either, we looked at either string where we had string error messages, but here it's more general, so you can specify the type of error messages, and then you can throw exceptions and also catch them inside the contract monad. So let's do a first example. Let's call it my contract 1. And let's say we don't want to write any state, any log messages, so we can pick unit there. Now we also right now don't need any endpoints, and for that there is empty. So we can specify the empty type, and that means no endpoints available. For error messages, a popular choice is text, which is a much more efficient type than string for textual data. So when you are dealing with large amounts of text or text in general, then text is normally a better choice than string. And finally, I don't want an interesting result, so I can take unit there as well. And the very first thing we can do is simply log a message. And this is not to be confused with making use of this W feature. This is just really logging, as we have seen before. So for that I can use contract log info, and now I need a string, or more general, I can use anything that's serializable that has a to.json instance. So let's say hello from the contract. And now the compiler is complaining, and it's complaining that it doesn't know what the type here of this literal string is. Normally, as I explained before, in Haskell, if you have a string literal, it's a string. But I activated this overloaded strings extension, which, as I explained before, allows you to use literal strings for more general textual types, including text or byte string. So the compiler at this point doesn't know what type this is. Is it a string? Is it a text? Is it something else? And in order to disambiguate this, I also added this type applications extension, which allows me to specify for a polymorphic function like loginfo at which type it is used. So loginfo is polymorphic and takes arbitrary serializable types, but I now wanted to use at string. And the syntax that is enabled by type applications is like so. So I can use the @ symbol and then the type name. So that means use this loginfo for type string. And then it's clear to the compiler that this literal string is indeed a string. Okay, if I want to test it, I also need a trace. Let's call it my trace. So that's of type emulator trace unit. And all I want to do is I just activate the contract. So I just activate contract wallet. Now I need to specify the wallet and the contract. So let's say wallet 1 and my contract 1. And finally, in order to test this, as before, I just use run emulator trace IO, my trace 1. It's still complaining, oh yes, because I'm ignoring the result, so I'm ignoring the handle. So this wouldn't be, this activate contract wallet wouldn't result in a unit, it would result in a handle, but I say it should result in a unit. So as before, I can throw away the result with void. Okay. In the REPL, let's load this module and let's try test 1. And as expected, we see the log message here. One thing I should still point out is I qualified log info with contract here, which tells that it's supposed to use the log info from plutus.contract. And the reason I have to do that is because, as we saw before, you can also log from the trace monad, and it's also called log info, but that's defined in control.monad freer extras. And in order to tell the compiler which version of log info I want to use, I qualify it here. So this is the logging from inside the contract monad. So next, let's try to throw an exception. So as I said, we can now have error messages of type text. So let's turn this into a do block and let's throw the exception before I do the logging. So this throw error allows me to throw an exception and of type E. So in our case, E is text. So I can specify text here. I can use literal strings because I have the overloaded strings extension active. So I can use a literal string here, which will then be passed as a text. So for example, I can say boom. Okay, and I also have to disambiguate this because in the emulator I also have the option, so I also have to disambiguate this with qualifying it with contract. Okay, and now it's complaining that this also has a result which I'm ignoring, so let's also do void. Fine. And let's try again in the REPL. I reload and do test 1 again. Okay, now we see the log message is not displayed anymore, but we see contract stopped with error and we see our error message, boom. So this behaves as expected, as you would expect of an exception, that execution stops at the moment an exception is risen. That's the same as we saw in maybe and in either. As soon as we got the left, as soon as something went wrong, the rest of the computation was ignored. So here, because the exception is thrown here in line 21, we never get to line 22 and we don't see the log message. We can not only throw exceptions, we can also catch or handle them. We could have done that with maybe and either as well, but let's just do it here. So let me just copy this and call it contract 2. And let's now change the error type from text to void. Void is a Haskell type defined in data.void that has no inhabitants. There is no value of type void. This is different to unit. Unit has exactly one value, which is also called unit. Void has no value. So what does it mean to have a contract with error type void? Well, it means this contract can't produce any errors. It can't raise any exceptions. Because in order to raise an exception, it would need to provide an error message of type void. But there is no value of type void, so this can't happen. So if we have a contract with an error type of void, we know this contract won't have any exceptions. It won't raise any exceptions. So what I want to do is I want to handle, just call contract 1, but handle the exception. And to do that, there is contract handle error. And if we look at the type, it takes a contract with error messages of type E and a handle. So if an exception is risen here in this contract of type E, then we have a handle that takes an E and turns it into a contract with a potentially different exception type E prime. And the overall result of this handle error construct is then a contract with error type E prime and the same result type. So what this will do is it will run this inner contract. If there is no exception, the result will be an A, and that will be the result of the overall computation. However, if there is an exception of type E, then the handle will be applied to the E, and this contract will be run instead. So in both cases, whether there's an exception here or not, we get something of this type. So in our example, the E is text because we will use contract 1 here, and the E prime is void. So we need to specify the handle and the contract we want to run. So the handle, it takes an error message of type text, and now we must write a contract, what to do if we receive this error message. So for example, I can simply log it. So I can use contract log info again, but I can also, just for variety's sake, use log error and now the error message. And I want to use a string, something like chord. Okay, and now I want to use the error message here. But this won't compile because error is of type text and this is of type string. And but there's a way to convert from text to string. That's unpack. That's defined in data.text. So that converts a text to a string. Note that in this case, I don't have to specify at which type I'm invoking this, as I did here. Here I had to tell the compiler that this little string is a string and not text or byte string. Here, the compiler can deduce that automatically because of this unpack. So it knows unpack as of type string. So this here must also be of type string, otherwise I couldn't concatenate the two. So this is of type string, so it knows I'm invoking log error at type string. Okay, and now I need the second argument, the contract I want to handle errors for. So my contract 1. Now in the REPL, if I reload and do test 2, I see I don't get an error anymore. So this contract 2 does not fail, but I do get the expected log message that I caught the boom exception. Also note that this is the only log message I get. So I still don't get this one. So what will happen is here in contract 2, when I call handle error, contract 1 will be run. It will throw the exception, but this won't lead to an exception in contract 2. Instead, the handler kicks in, takes the error message, which is boom in this case, and then simply logs it to the screen. So my contract 2 will run without an exception because the exception risen in contract 1 is caught. One other thing I should mention in the context of exceptions is that there are other ways in which they can arise, not just by being explicitly thrown with throw error. So there are certain operations that you can do related to the blockchain that can result in exception. Of course, maybe internally in the implementation of those operations, throw error is used, but that's opaque to the user. So for example, if you try to submit a transaction, that can fail and result in an exception. And the reason is that something can be wrong in the way you constructed the transaction. So for example, the way it works in Plutus off-chain code is you don't directly give the transaction. Instead, you specify certain properties that the transaction should have. For example, you can say this transaction should pay 100 ADA to that address. And then the algorithm will try to construct a transaction with this property. So in particular, in this example, it will look at the UTXOs that belong to you, that are in your wallet, and find enough inputs to cover these 100 ADA plus fees. And if your wallet doesn't contain enough funds to pay 100 ADA to that address, then that step will fail. And then when you try to submit the transaction, you will get an exception. Let's talk about the second type parameter, the S next, which specifies the endpoints. So the way this is normally done is that we define a type synonym and call it something with the word schema in it. But of course, that's just a convention. So let's call this my schema. And if I want one endpoint that takes an int and is called foo, the type is endpoint, then a type level string, and the parameter type, so int in this case. So this is a type. It's a type, and in particular, this string here is a type. So that's why I say type level string. So it's a string used at the type level. So that's some fancy Haskell extension that's enabled by data kinds. Okay, and now I can define my contract 3, which is now of type contract unit again for the first, but now no longer empty, but now I can use my schema. I could, of course, not have done this type synonym and at this point directly written endpoint foo int. Now for error messages, let's use text again and let's say no result type. So what can I do? We have endpoint, and that just results in a contract of result type A, provided we have this restriction here, this constraint on our schema type S, that it has an endpoint LA. So L is the label, that's the name, and A is the result type. So if our schema S has an endpoint with parameter A, then this endpoint computation, monadic computation, will give us a contract that results in an A. So I have to specify which endpoint. So that's the same add here again, but now it's specified by its label, by its name. So foo in our case. And so this is a monadic computation that will block contract execution and wait for a value to be provided. In our case, a value of type int. Once that value is provided from the outside, this results in that provided value and we can bind against it. So what this will do, this contract, it will block until from the outside this endpoint is invoked and provided with an int because we said it would be an int. And at that point, it will continue and n will be bound against the provided int. So to try it out, we can use contract log info again, n. N is serializable, so we can just use n there. And the compiler knows it's an int, so we don't have to tell it. So in order to test this, now it's no longer enough to simply start the contract, because as I said, if you just start it, it will block and wait for an endpoint call. So this wouldn't do much. So let's also turn this into a do block. And in order to invoke the endpoint from the trace, we need the handle. So I can no longer ignore the handle. I actually need it. So let's call it h. And then, as we have seen before, I can use call endpoint. I must say which endpoint. So add foo. Then it takes the handle, and I must provide the parameter. So an int in our case, for example, 42. And this should work. If I reload in the REPL and call test3, then we do see here the contract is started. Then it would block, but we receive this endpoint call from the outside, from our trace monad in this case, with 42 as a value. And then we see that it works, so the contract receives the 42 and then logs it. So what do we do if we want more than one endpoint? In that case, this type here, the schema, needs to be more complicated. So we have to specify more endpoints. And we do that by chaining them together with this so-called type operator. So a type operator is an operator that operates on types, as the name suggests. So it takes one or more types and combines them to a new type. And in order to do that, we need this type operator extension. So we can now specify another endpoint. Let's call it bar. I don't know, of type string. And let's just basically do the same here with bar. So let's call the string s and log that as well. And in our trace, if we want to try it out, we also have to call the second endpoint. So in this execution, the contract will run, will block here. Then when this endpoint call comes, this will unblock and go to here and then block again. So if we do a second endpoint call, now we need a string, Haskell. Then this should work out. Let's try it. And indeed, we get 2 log messages now. Here's the contract log with 42. And here's the contract log Haskell. I have no idea why we get the 3 stars here and not here. But nevertheless, it seems to work. So here was the endpoint call on foo with 42. And we get the log message. And here is the second endpoint call now on bar with the value Haskell, and we also get the second log message. Finally, let's look at the first type parameter, the writer. And so this W can't be an arbitrary type. It must be an instance of the type class monoid. This is a very important, very common class in Haskell. And it has mempty and mappend. Mempty is something like the neutral element, and mappend combines 2 elements of this type to a new element. The prime example of a monoid is lists, where mempty is the empty list and mappend is concatenation. So, for example, I can say mempty list of ints, it will be the empty list, and I can use mappend 1, 2, 3, 4, 5, 6, and it will combine them. But there are loads and loads of other instances of this monoid type, and we'll probably see other instances in this course. But for now, let's stick with lists. So let's try this. So my contract 4, do want a first argument, and it must be a monoid, so let's use list of ints. Schema, we don't want any endpoints, so we can just use empty. Let's use text result. Okay, so let's start with a weight of n slots, 10 slots. We are not interested in the result. So now the way we write to the state, to this log, is with tell. That comes from the monad writer class, and contract is an instance of it. So now we need some list of ints. So for example, the list that just contains 1. Now let's wait for another 10 slots and do another tell. Let's say the list that just contains 2. And let's wait for the final 10 slots. Now for a trace that exercises this contract, we start as before by starting the contract. Now let's wait for 5 slots. Now the way we read the state of a running contract is by observable state, and as argument it just takes a handle, which we called h, and the result will be the state at that time. Let's call that access, and let's log that from the trace monad. Okay, and let's do that 2 more times. the second time, let's wait now for 10 slots. Let's call the result y's and lock those. And the final time, again 10 slots, let's call the result z's and lock those. So this should be like interleaved, right? Here we wait 5 slots, that's before the first tell happens here. So this should be after the first tell has happened, but before the second tell has happened. And this should be after the second tell has happened, but while this is still waiting here. Oh yeah, and I get the warnings because I should ignore the result here of the wait. Finally, again, let's also have a test 4. And test it. And let's check what we get. So the trace waited for 5 slots. So this is the first time we call this observable state. And we get the empty list. So before we use tell, the state will be the mempty of the monoid. And as I explained, in the case of lists, the mempty is the empty list. So before there has been any tell, the state that we observe with the observable state will be the mempty, the empty list. So now by slot 10, the first tell happened where we wrote the list that contains just 1. So if by slot 15 we observe the state again, now we get the list just containing 1. Wait another 10 slots. Here in the middle, the second tell happened. The list just containing 2. And now we get the list containing 1 and 2. So what happens is each tell uses mappend of the monoid that we are using as W to mappend the told thing to what's already there. So it starts with the empty list, then this is concatenated with the list just containing 1, which of course is the list just containing 1. And then after the second tell, the list just containing 2, that is concatenated with what we had until then, the list just containing 1, and we get the list containing 1 and 2. So this is how this works. So how the contract can communicate information to the outside world that can then be observed with observable state.